Now let's have a look at this problem. Now this is kind of the second part of that same problem that I discussed in the previous video. So here we are taking this as our series, right? And the question asks, how many terms are required to ensure the sum is accurate within 0.0005, right? Now you should be familiar, like you should get used to this terminology as well, right? Now, so it says, now see, in the previous problem we said that if we take 10 terms, then the error of this 10 first of the addition of this first 10 terms will be at most 0.005. That's what we basically did, right? So here it's asked, like in this question it asks how many terms, that means how many terms that we have to add so that the error of the addition of those terms will be less than 0.0005. So this should be much more accurate than this one, right? So now as we already have a inequality for any given remainder, we can easily figure out the suitable n value, right? And the inequality will be this one, okay? And also be careful when you are using this function fx, you must at least mention all those conditions that we need, right? That is continuity, that the decreasing property, and the positivity, right? So you should have all these conditions satisfied in order to use in order to write this inequality, okay? Having said that, we also saw that the integral can be reduced down to 1 divided by 2 to the power n squared just by computing the improper integral, right? Where fx is equal to x cube. Okay, so then here what it asks is that how many terms are needed, right, to ensure this accuracy. That means how many terms we need so that when we add all those terms, the error for those terms should be less than this one, right? And we already know that error will be less than this one. For any given n, the error will be less than or equal to 2n squared. So if we find a suitable n value, so that this term is less than or equal to 0.0005, okay? So if this term is less than this one, then for that particular n value, remainder will be less than this one. In other words, if we add that number of terms, this number of terms, then the error caused by adding this number of terms will be less than this one, right? So to find the n, you just have to evaluate the given inequality, right? So the inequality, you can even rewrite it as for this one you can write it as 5 divided by 4 zeros, and it will be like this, okay? So if you solve the inequality, you will end up with this one, right? And from the calculator, you can say that the square root of 1000 is equal to 31.6, okay? But we know that n is a integer, right? It cannot have all these decimal values, okay? But from this inequality, what it says is, if n is greater than this number, we have all these required situations, right? So what we can simply do is, we can choose a number, an integer greater than this one. Let's take n equals 32, right? So if we take n equals 32, then this n will be greater than this value. So it will satisfy all these conditions, right? So by going in the reverse direction, we have this one, right? So basically what we have is, for S32, that means if we add the first 32 numbers, then the answer for this one and the difference between this one and the actual answer, that means the error of adding the first 32 numbers, that is represented by R32, will be less than or equal to 0.0000. I mean, there are 3 zeros, 0.0005. Okay, right? So that's the answer that they require, that they are looking for in this type of a question, right? So we found how many terms we have to add so that the accuracy lies within this value, right? So in a different way, if we rephrase our answer, we can say that if we add the first 32 numbers, then the error between, or the difference between the actual answer and this one will be definitely less than or equal to 0.005. But still we don't know the actual answer, okay? We have, what we have is a kind of a comfortable region where the actual answer should lie, okay? Right. And in the next video, we will do some fine tuning for this inequality in order to get some better results.